Hi, chemistry students. Welcome to our next Vodcast. This one's on matter. So we've talked about combustion, but in order for things to combust, we have to have those molecules somehow being changed or rearranged. And so we're going to talk about how this occurs. We tried to draw what we envisioned combustion being earlier on, but we haven't really talked about matter. And that's this next whole chapter. What is matter and how does it change? So let's take a little step back and start with matter. Let's look at the ocean. Here we go. When you look at the ocean, what here is matter? Think about that for a moment. It may be obvious. You're like, well, the fishes matter, maybe the corals matter, but is everything matter? Let me ask you some questions. Is love matter? Now, I guess you're going to say no, so that means everything is not matter. Are flames made up of matter? No, we did talk about that in the candle lab. They're made of waves of energy. So not everything is matter. In that case, just the coral and the fish and the water. There was a lot of matter in that picture. Okay, properties of matter. Chemistry is the study of matter and energy. And so that's how we're starting with this chapter on combustion. Relates a lot to matter. Write down that word mass. There we go. Matter has uniform and unchanging composition called a substance. Now, that's kind of a vague term, substance. So when you think about table salt in your mind, you're like, oh, that's what I put on my French fries, or water, and you kind of know, well, it must be something that has identifiable properties. Hence, it makes a substance or a pure substance. Because you can identify those things in your brain, it signals that you know what it is. So we do call it a pure substance. But if we talk about seawater, look at our pictures here. When we talk about seawater, you might envision great waves on the beach, or a tropical beach, or maybe the San Francisco Bay. Looking at these three pictures, they're all made of seawater, but they look very different, don't they? So we would not call them pure substances. Seawater can vary from place to place. So even though water might be a substance, we wouldn't say seawater would. There are variations. Okay, how do we observe physical properties? It's when we observe or we measure matter, and it doesn't get changed. So can you think of some observations that you can make that really don't change the substance? I think you can. Let's watch a video and we'll learn some more. As you hear the video, you can write down here in this spot what some of these examples are.
Physical properties of matter include melting point, boiling point, color, density, magnetism, crystalline shape, malleability, ductility, luster, and refractive index. The physical properties of matter can be observed without any change in the matter's chemical composition. Chemical properties, on the other hand, can be observed only when matter undergoes a chemical change. Here are some examples of chemical properties. Hydrogen peroxide decomposes easily into oxygen gas and water. Iron reacts with oxygen to form iron oxide. Sodium metal reacts with water to give off hydrogen gas. Sodium hydrogen carbonate, baking soda, reacts with acid to give off carbon dioxide gas. Lead nitrate reacts with potassium iodide to form a yellow precipitate of lead iodide. Red phosphorus can undergo combustion in air.
So that was a bunch of physical properties and chemical properties. So you can write a few down. Pause if you need to add some to your list. So one of them that they talked about was a change of state, also known as a phase. So you know when water boils, liquid water is the same as water vapor. Think of it this way. Liquid water is made of H2O, and water vapor, or steam, is also H2O. So therefore, it's not changing its chemical composition. So it's a physical change or a physical property. So thinking about phase changes, solids, liquids, and gases, I bet you can draw them for me. Why don't you try that? Push pause, draw it, and tell me how those molecules move. Go back to first grade. Did you learn a song about how the three states of matter look and how they move? Think about their energies as well. Those are all important. Draw and then check your answers. Is this what you drew? Notice here we have as a solid, it's not like a cube. You don't see all the individual molecules lined up here. We actually have a force of attraction, that's this line right here, in between the two water molecules. And this is what keeps it as a solid. There is a strong force of attraction between one water molecule and another. It's actually between the hydrogen and the oxygen. And we'll talk about hydrogen bonding later on. But this keeps it in this uniform pattern that you see. And here we have very little movement. They will vibrate back and forth, but it keeps it as solid ice. And notice there's space in the middle. That happens to be very unique, unlike other solids. If you looked at a metal, metals that are solid might be just simple circles like this. And we'll talk about metallic bonding and why it looks that way. But here's water. You're familiar with ice. Here's a liquid. Notice here the force of attraction. There is some force of attraction, so the molecules can slide past one another. And then in the gas, there is little force of attraction. They actually have completely elastic collisions, and they're free to bounce around. So solids in this ice cube are a uniform shape. Liquids take the shape of the container, and gases will fill up any area that they can occupy. Which one has the most energy? The one that moves the most, the gas. What about plasma? That's not what we commonly see, but it does exist. So when we talk about the three states of matter, we're talking about solids, liquids, and gases. But I do want you to be familiar with plasma, and it's another state of matter. And there's a couple more that are even more interesting and unique. We probably won't talk about those, but let me show you.
Hi, I'm Emerald Robinson, and in this What Is video, we're going to investigate the state of matter called plasma. Plasma is the state of matter that consists of a mass of free electrons and positively charged particles called cations mixed together. Plasma has neither a specific shape nor a consistent volume. In other words, plasma can easily flow into and take the shape of a container and will expand, redistributing itself to evenly fill that container. Although the properties of plasma are similar to those of gases, plasma and gases are not the same thing. In plasma, electrons are released from their orbits around a nucleus, creating a soup of free electrons and nuclei. Because these charged particles are loose, plasma easily conducts electricity and both produces and responds to magnetic fields. Plasma is created when a gas is either exposed to a high temperature or when high voltage electricity is passed through it. The heat or electricity makes the atoms in the gas move so quickly and collide so violently with one another that electrons are knocked from their orbits. Because of the way they are created, plasmas are sometimes called ionized gases. Although plasma isn't discussed as often as solids, liquids, and gases, and was the last phase of matter discovered, you're probably more familiar with plasma than you think. Plasma gives neon and fluorescent lights their glow, is formed during lightning strikes, and of course is present in plasma televisions. Chemists also classify fire as a plasma. Plasma makes up our sun and is visible in the solar flares that erupt from its surface. Because plasma is the stuff of stars, it is the most common state of matter, making up about 99% of the observable universe.
So, now you know what plasma is. You know, there's a couple other that she said didn't exist. There were only 4 states of matter. But there's also a condensate of a Bose-Einstein or condensate of Fermi. Very strange, unique states of matter under very rare conditions. So we're not going to encounter them or discuss them too much. But you can look them up. Interesting stuff. Now, one other thing that you may not have been exposed to in middle school or in integrated are physical properties that we call intensive or extensive. So you can write some examples down here. But extensive properties depend on the quantity of the matter. So if you have a big chunk, it means that it's really massive, and we describe that as an extensive physical property, like mass, volume, length. It actually changes. Where intensive properties never change. You look at the density of water, and it's 1. Doesn't matter if it's 1 drop or 2 liters of water. Big or little, the density is still 1 gram per mil. It doesn't change. A big red apple, small red apple, not going to change. So boiling point, melting point, specific heats, all kinds of things that are intensive. They don't change where you have a little or a lot. So intensive and extensive physical properties. Chemical properties, well, you already saw in the video, the ability of substances to combine or change into 1 or more other substances. So do they react with acids? Are they easily combustible in alcohol versus water? What is the combustibility of those chemicals? Do they react with oxygen? Do they rust easily? Do they oxidize? So in order to describe these physical properties, we can actually see if matter itself might change physically or chemically. We already alluded to that with our change in state. So physical changes change without altering the composition, like we talked about with water, liquid and vapor. Here are some examples. The state and change in shape. If you tear, rip, or grind, you'll see in the lab in a few minutes. Or dissolving. That one's kind of unusual, but think about when you dissolve a salt crystal, it is actually breaking apart, but it still tastes like salt. It retains the same properties. So we say it is a physical change. Dissolving is a physical change. Chemical changes will change into a new substance. So in order to describe it, if it gets completely rearranged, if we have magnesium combining with oxygen and it combusts and you get magnesium oxide, you have a completely different compound. So therefore we say it's a chemical change. When things oxidize, iron rust, you get oxidation, you get iron oxides, fermentation, turning into an alcohol, corrosion, reacting with acids. These are all chemical changes. How do we know? Well, in the lab that you're going to do this week, you will have lots of examples. But if I take 2 liquids and I mix them together and I get a precipitate, boom, we see a solid form. Then we know we have a chemical change. That's a huge evidence for a chemical reaction. Leaves changing color. So a lot of times when you see a color change, you know that a chemical reaction has actually occurred. Photosynthesis slows down, and photosynthesis is a chemical reaction. You see the pigments shine through when the length of the day changes in the fall. Evolution of a gas. We mix 2 chemicals together and we see bubbles arising. We know that probably a chemical change has taken place. Here you have a metal put into an acid. Whenever a metal combines with acid, we get hydrogen gas. And how about heat and light? Obviously, that's chemical reaction. Something exploded there. And that's a good indication. Now, the last thing I want to mention is when matter gets rearranged, we don't create new matter and it doesn't disappear. Antoine Lavoisier in the 1700s showed us that if you burn something, he looked at mercury 2 oxides, if they burn and I collect everything that comes off, then it weighs the same after as it did before the chemical reaction. Here's an example.
The law of conservation of mass states that in a chemical change, matter is neither created nor destroyed. It is only rearranged. For example, let's place 5 zinc and 5 sulfur atoms onto the 2 sides of a pan balance. The 2 sides balance because the contents of each pan are identical. Consider the reaction of zinc with sulfur atoms on one side of the balance to form zinc sulfide. 5 zinc atoms will react with 5 sulfur atoms with a tremendous release of energy to form 5 zinc sulfide molecules. The 2 sides still exactly balance. The total number of zinc and sulfur atoms on each side are still identical, demonstrating the law of conservation of mass.
So that was pretty remarkable for back in 1700s. Lavoisier was actually a tax collector, and he was an early alchemist who did this in his house, in his lab in his house. And he, like I said, he burned some mercury compounds in order to show that the mass before and after are equal. So there's a little equation for you. The mass of the reactants before, easy to collect that data, and then when he burned it, he put it in a container that he could actually show the mass of the products after, which in his case was mercury and the oxygen gas. People used to think things just disappeared, but if you collected it, he showed the mass of the oxygen gas produced and the mass of the mercury equaled the mercury oxide before he started. So matter is neither created or destroyed during a chemical reaction. Mass is conserved, as well as energy that gets transferred. And we'll talk about that theme as well throughout these chemical reactions you do throughout this lab in this chapter. All right, that's it for now. Bye.